Let's get started. So today is the day. Yes. Sorry that I had to cancel the lecture on Thursday. So as we planned, well, I don't know if it was planned, but as I said, after this we will have the two makeup lectures in the evening from 7:30. It's going to be in the second floor of this building. Okay, from 7:30 p.m. till sometime. Okay, when we get out of the room, it's LED reduction. Okay, so if you grab that thing on your hand, that's when you leave. Okay. So now you understand why the formulation of the perturbative, not necessarily perturbation theory, but formulation of the theorem metric. Okay, so that's the plan. And a couple of announcements. After this lecture, I will post last year. Again, it's going to be, basically checking some of the exam problems in the books and think about some of the parts that I didn't cover explicitly. And then lastly, we will have a final exam sometime next week. Do you know which day that is? Okay, I will post this soon. Probably, I don't know, sometime either Monday, Wednesday during our lecture time for 3 hours, something like that. Okay. I encourage you to come, especially if you're registered class. Even if you aren't, you're welcome to come. Let's see. The format in class exam. What do you expect? Closed book? Necessary formula will be provided. You will just get distracted if you just have a whole book and a lot of formulas in front of you, right? So it will be better to be guided in each problem. Okay? So closed book, necessary formula will be provided. I'm not checking the memory here. Okay, I hate Korean education with all memorizing stuff. Okay, I'm not good at that. So it's more of understanding things and actually think about the physics that we covered. Okay, what kind of problem? I have no idea. I haven't even started making problems. How many problems? Good question. I don't have an answer to that question. So we'll see. Okay, so hopefully this will give you a chance to go through the entire semester of materials. That's the thing, right? So that you get a chance to think through all those processes. You start, hopefully you have a comprehensive picture, okay? That's what you gain by having an exam, not the evaluation part. Thank you very much. And also, can you check if this room can do recording of the lectures? Oh, when you get a chance, okay? What else? Oh, last thing probably, course evaluation. So I don't know if you received email or anything from the system or department yet, but at some point I know that there's going to be such a thing. So please consider to submit your course evaluation. Okay, I'm not asking to give me good thing. Okay, that's not the point. Just give your own thoughts. Okay, so that I'm gonna teach you up to 2. So if that's a miserable decision for the department, you have to stop. Or if there's a good decision, you have to explain. Or if you expect some improvement, you have to explain. Okay? So it's feedback so that I know what can be improved, which aspect can be modified, and so on and so forth. Okay, that's the whole point. Okay? To improve the course. So please spend, I don't know how many minutes you need, maybe 3 minutes, right? Sit down, click, write on something. Okay? Maybe it was too slow, maybe it was too fast. Maybe it was too detailed. I understood everything. Why I don't know why Professor spent so many times explaining every single detail. That's a good comment, right? Or you can say, oh, it may be good to supplement with something else, whatever. Okay, the point is to provide your feedback. Okay, so that hopefully things can be improved next time. Any question? Yes.
시험 아마 월요일이 될 것 같은데
Okay.
12시부터 저희가 제가 조교 활동 때문에 시험을 그날 오전에 감독을 하는데요.
Yeah.
이제 아마 12시 반에 끝날 것 같아서
Okay.
시험을 볼 때 점심을 여기서 먹으면서
Sure. No problem.
네, 알겠습니다.
Yeah.
감사합니다.
Eating is no problem to me. As long as it is not, in conflict with whatever regulation that department has, I don't have any problem. Okay. Unless you're taking a bath while you're taking exam. No, other than that, I'm good. Any other questions? Okay, good. So everything's clear? Makeup, final, course variation, what else? At least that's our goal. That's it. Okay, so last time, first of all, we derived a transition probability. So super quick summary that we move. Transition probability for unit I, and that had a form that we talked about this. So for every final state, we had E final, and then we had to the fourth total momentum conservative function. So that one big factor. And then in fact, we call this big factor kinematic factor D. Then for initial state, we walk through that, there's only that factor, and then amplitude squared. And from this, first we derived a differential decay rate, which was given by 2 times of decay particles energy. And then obviously amplitude squared that you can compute, and then okay. So D is for one particle decaying into whatever n number of particles. And then we also derive differential cross section that requires not only just probability per time, but it also needs a probability per time per flux, right? When you shoot the particles from the target, there was no bit of flux. But because of that, in addition to this sort of factor, there was an extra factor. So first of all, we have 2 particles in the initial state. So we have 4 times E1 and E2, and that flux part that looks like this. And then the rest is the same. So basically amplitude square, then corresponding kinematic factor for your final state, right? So that was what we talked about. And I talked about the fact that decay rate is 1/lifetime, and we talked about the fact that this is Lorentz invariant, this is Lorentz invariant. Look at that. This is Lorentz invariant measure. This is Lorentz invariant delta function. So we discussed that this is only Lorentz non-invariant vector. In fact, it transforms in a way that you expect for gamma because you want to see time dilation. We saw that. Now let's finish the discussion about the cross section by first looking at whether this transforms under the Lorentz transformation in a way that you want to see it. Okay, and then we're going to look at the case where final state has 2 particles. Okay, so that will be the remaining discussion for the class. So let's first talk about how cross section transform under the Lorentz transformation. Okay, so to this end, first of all, I think I showed that the mass dimension of the cross section is actually -2, right? I showed that last time. I showed that this has dimension 1, therefore it has 1/time, it has dimension -2. So it has a dimension of area. Okay, so it is a cross-sectional area. So when you have a particle and then hitting some target with a cross-sectional area, you literally will see that area. So you see that if you boost the system along the propagation or collisional direction, obviously you expect that the cross-sectional area shouldn't change. But obviously, if you boost the other direction, things can change. So you will hope that you expect that therefore this formula captures the property. So if you boost the system along the collisional direction, you hope that nothing changes. But you hope that you hope to see that this will change if you boost along other direction than the collisional direction. Okay, so that's the thing that we want to check. So to this end, let's also quickly note that these 2 factors are manifested in Lorentz invariant. But again, this is invariant Feynman amplitude. This is Lorentz invariant kinematic factor. So therefore, this free factor is the only thing that we need to look at to check the Lorentz transformation property of the differential cross section. Okay, so let's do it. So what is this factor? So E1 times E2, then B1. So let's first understand it. So energy in relativity is gamma times mc squared. Okay, which is gamma times m. And momentum, some direction of pi is gamma times m v. Right? Remember that. Wait. So that means velocity in component is given by pi over energy of the particle. Right? Good. So let me use that to rewrite this as. So first of all, let's assume that we are going into the regime. Let's go to the frame where it is hadron collision. Okay? So we are in the center of, if you like, it doesn't need to be center of momentum frame. What I'm saying is I want to go to the frame where they are collinear. So either they're colliding this way so that their direction of momentum is the same, or one guy is trying to escape, the other guy is really chasing to hit the back. Okay, either way, I want to go to the frame where momentum direction is aligned. That's where I want to go. So that direction, let me just call that to the x direction for now. So that means that I can write this as E1 times E2, and then this is like first particle's x momenta divided by energy of that thing, minus second particle's x momenta, because that's the whole momenta along that direction over energy of that particle. Okay. So once you do that, then that is equal to E. Let me write better way. 1x E2, and then E1 E2x. Since I am in the frame where everything happens along the x direction, as I explained, you expect that nothing changes if you boost along the x direction. You don't see that something changes if you boost another direction. Right? So that's the property you'd expect physically. So in that sense, assuming or nothing changes along y-z direction, meaning y-z components are fixed. That's what I mean, basically. Y-z components are fixed. So I'm not going to touch y-z components. I can rewrite this expression as 2, 3, which is y-z components, then mu, and then that is 1, 2. Mu, sorry. I meant E2 U. Okay, so this is literally cross product. That's what I'm saying, and I just wrote in a 4-vector sense. But this expression is true, obviously, if I say, oh, I'm not going to touch 2, 3 component, but I'm happy to touch first, second component, which is now this can be touchable 0 x direction. And if you consider what are the possible Lorentz transformation along the 0 or temporal component and x direction, that is the boost along the x direction. And indeed, this expression is manifestly invariant if you do boost along the x direction. And cross section does satisfy that. Okay? And I think you can play more. Actually, you can actively boost along the other direction, just like if you have a particle, and then say there's a target which has some shape like that, and obviously along this direction of collision, there is well-defined cross-sectional area like that, and that doesn't change. But obviously, if you try to boost other direction, the cross-sectional area along that direction will not change, but obviously that direction can change. Okay, so this formula, and this I'm showing that it does have the property, correct property that it needs to be for cross-sectional area. Okay, any other question? Yes.
So are you saying that that quantity is not Lorentz invariant?
It is not.
Then that part is other parts of Lorentz invariant. Then the sigma is not Lorentz invariant. You were saying.
Yeah, it is not Lorentz invariant. It is only invariant along boost along the direction of collision, which needs to be, because if you have a collision and see that cross-sectional area, even if you go fast or slow, nothing changes that area. But obviously, if you boost along that direction, lengths along that direction can contract. So that information is not meant to be Lorentz invariant. So, right, exactly. So the perpendicular area doesn't change, but it can contract. So, so the cross section is not Lorentz invariant, but it is invariant under the boost, which is all that matters if you want to measure the cross section. Okay. One more thing that I want to compute about this expression is the following. So now, which we will use later. So now let me go to the center of momentum frame. If I go to the center of momentum frame, then say momentum of the first particle is like E, along E hat, and the second particle is minus of E hat, right? Then we see that this formula becomes E1 plus E2, and then P hat. And that's nothing but total energy in center of mass frame, and then some, absolute magnitude of the initial momentum. Basically. So this free factor that appears in the cross-section formula satisfies this relation or this expression in center of momentum frame, which is total energy times the momentum of the initial particle, colliding particle. Good. So we understand the Lorentz transformation property of cross-section, and the last thing I want to talk about this cross-section, at least this part of the discussion, is to actually compute this kinematic factor when there are only two particles in the final state. Okay. So we are talking about now two-to-two scattering. And then we want to have analytic expression. So let's talk about this. Okay, so cross section is given by that factor that we know. And then, oh, I should not take this out. Can I? Yes, I can. I can. So, since we're talking about two, let me talk about 1, 2, 3, 4. So 3, 4 minus 8 particles. And there's one momentum conserving delta function. Final, initial. Should I write that? Yeah, I have to write it. Better 3, 4, 1, 2. Then 2 to the scattering angle, depending on the theory. So now I just want to see whether I can evaluate this kinematic factor phase-space integration. Okay, without needing to know the details of this, which is theory dependent quantity. Okay. Okay, so the first step is let's split the delta function into a temporal component. So E3, E4 minus E1, E2, but that is not what's known as ET, right? Total energy. And then there's the 3 momentum parts. 3, 4. And then let's just go to the center of momentum frame. Okay, so when I do it, I went into center of momentum frame. So the first thing I want to do is I want to just use this factor to evaluate this three delta function. Okay, so let's do that. So I have 2 pi to the 4, I have a 2 pi to the 3 sitting down. So should I carry all this back all the time? Let's do it. Yes, let's do it. So I already told you that this factor is the same as total energy times initial momentum. Okay, so that's it, is enough. Enough. I can write it down all the time. Although, well, let's see at some point. Okay, so there is that. My dot was combined 4 times E3, E4. So I just provide all of that. So 2 pi to the q, 2 pi to the 4th. So I'm left with a 1 factor of 2 pi. I haven't done anything with this, so I still have that. And then I finished up that calculation, right? But now, when you look at this expression, obviously, whenever you see P4, you must say that that is nothing but minus P3, right? Because I haven't done the calculation. Let me just write that way. And then there's this net result. Okay. Good. So now I just need to do that calculation. Now remember, now this is a function of P3. So now this is a function, some gigantic function of P3. So now you know that if you have a delta function, which is a function of something, then you know how to do it. So if you understand the zero of this function, that's 0. Let's call that there are a set of x0 where f of x0 is 0. That's what I mean by 0 of f of x. Then it is 1 over derivative of that thing evaluated at 0. The absolute value sign and delta of x minus this. Sum over that. Okay, so you have to see this formula. So we're going to just do that for this integration. Question so far? Okay, so before that, let's rewrite this major part as follows. So if you have these 3p, that is, well, 3y, EP, 3 square, and then angular part. Okay? Yes. Oh, yes. All right. Let's see. Okay, good. So therefore, that part, so therefore, the integration we have to do, this part can be evaluated as, let me just write it out and then evaluate first. The function, which is t, so that is function divided by that with respect to integration variable, which is dp3, and then I'm interested in getting inverse of that, right? So that is this, right? Good. So let's compute that. So what is E3? E3 is square, that is the square. M3 squared, P3 squared. Right? Let's do it simultaneously equal. M4 squared, P3 squared, because of the first delta function calculation. Yes? So 2E3 E3, so that's the separation of that is to P3 P3. Exact same thing here. So 2E4 E4 3. Okay, so that means that object which appears here is same as P3. Whenever you, by the way, whenever you see P3, I meant absolute value of the 3 factor. That's what I meant. Okay, so I'm just sloppy in writing this way. But whenever you see P3, even here, right? That means absolute value of the 3 point. So by dividing by here, I get this is equal to this, and then you get the exact same thing. So E4 divided by P3 is equal to P3 divided by P4. Good. So now you just combine these two to get that expression. So therefore, that thing is this is the number, so it doesn't matter. Yeah. So what do I get? What I get is inverse of P3 over E3 plus P3 over E4 inverse, and that is E3 E4 divided by ET, and then let me just write more partially that. Okay, so now let's combine everything. Let's combine everything. So cross section becomes that thing is gonna cancel this thing. Okay, and then there was a 1 over 2 pi to the cube, which cancels 1 factors of that by this. So I get, first of all, 4 times ET I vector, that's the prefactor that we started with, and then 4 times 2 pi square from 2 pi stuff. E3, E4 canceled by this factor, so I'm not gonna keep track of that. And then let me write down the measure, which is dP 3, and then 1 factor of P3 cancels that vector, so I will get P3 vector, and then the omega cube, and then from the first calculation, sorry, I had not from the first calculation, I had that vector, so I'm going to combine all of that, which will give me EP squared P initial vector. And then whatever delta function I'm supposed to do. So it is a P3 minus P3 0. So hopefully you understand this notation is that this is like this x0. Okay? When the argument becomes 0. And then this vector delta. So yes.
Shouldn't be only one kid there? I don't know why there should be k squared.
Because one from the delta function one from the delta function, another from the ET that was sitting from in front.
So you got that also. There.
Oh, I'm sorry. I'm not supposed to write again. Yeah, you're right. So then let me just write that for now. Okay, so that's only from the delta function. Thanks. Any other question? Okay, so I can just finish up the dP3 calculation by doing so. So then I'm left with, now I'm gonna combine everything, 64 pi squared ET squared, and then the omega is final, and then let me just write as a final P momentum, this P3 is final, and then initial momentum, then that's the momentum. Okay, so that's the result. So let me write in a slightly better looking expression. So the differential cross section for 2 to 2 is given by 6 4 pi square ET square. Did I write ET squared? Yeah, I did. The final moment divided by each. That works out. Okay. Good. So that's very simple, nice looking expression. So first of all, let's check dimension, whether it makes sense at all. Okay, I know that this is dimension minus 2, meaning dimension of area. This is the angle, right? This is dimensionless. This is dimension minus 2. Everything I wrote manifests in such a way that these factors are dimensionless, and then the 1 over e squared is dimension minus 2. So it goes up. Good. And then let's consider first elastic scattering. Let's consider two cases. Let's see if it makes sense. Elastic scattering, if you just collide and just keep going, that means that the final momentum same as initial momentum. Okay, it's elastic. So basically, there's a nomenclature. Elastic means that the initial state is same as the final state. So if you shoot an electron, you want to see the electron comes out. If your muon comes out, that is called inelastic, something new happened. Okay, in this case, I mean, elastic scattering happens in most of the cases in non-relativistic, like quantum mechanical system. Like you have a degree of freedom, and then non-relativistic. Therefore, you don't have enough energy to produce new particles. Okay, so all you can do is that you kick a little bit, and then give a momentum transfer to some system, and it comes out. So that is what is called elastic scattering. And if you look at that formula, then well, you get expression with that. Okay, so that's the answer. Good. So then let's look at the inelastic scattering. In this case, in general, final state is different from initial state, and so final momentum is going to be different from initial. So you just take this expression as it is. Now, one point I want to make with that expression is that so let's consider, let's see, we talked about something like pi goes to nucleon and nucleon, or vice versa. Let's look at this diagram. So in the theory that we talked about so far, for instance, we have a diagram like that looks like this. Okay, you have seen this diagram before. So there is a pi, and then anti-nucleon comes out. And then pi has a mass little m. This nucleon, anti-nucleon has a mass capital M. And then if you try to write down the amplitude for this process, either that way or that way, you find that the amplitude goes like basically this propagator times 2 interaction coupling constant, right? So basically you get minus Ig squared because it is the 2 vertices, and then I over momentum transfer P minus capital M squared. So that is amplitude, right? Now, why am I writing down this expression? The point is that this looks like the same. Either I look at pi goes to n bar, or n bar goes to pi. In other words, this theory has time reversal invariance, secretly or explicitly. In other words, if you look at the theory that I wrote down, three different kind of scalars, the only thing that I wrote down is like psi that. Okay, and this preserves time reversal symmetry. Hence, the dynamics controlled by that thing does satisfy time reversal invariance, as you see, for instance, from this example. Okay, so it gives me exact same answer. However, so therefore, amplitude respect that symmetry, as you see, but that doesn't mean that the cross section is going to be the same, because cross section is a dynamic information multiplied by kinematic information. Okay, so dynamics may respect the symmetry, but kinematics can be different. Especially in this case, it's going to be different because they have 2 different masses, for instance. So if they have 2 different masses, this can be different, right? If you have like 1 eV electron versus 100 GeV guy. So if you try to collide 2 eV electrons to produce 100 GeV guy, okay, you have to work very hard, right? You have to carry enormous kinetic energy to produce it. But if you have a 100 GeV guy, just drop it, it's nothing to produce 1 electron volt guy. So the momentum can be extremely different in that case. So disparity in the mass can produce huge difference in the kinematic. So this factor is not equal to 1. In other words, this is different from what I'm trying to say is that amplitude can be the same in this case because of the symmetry. But the differential cross section can be very different. And this is useful to know because just by checking this, you don't want to say much about the symmetry. You have to be careful. Okay? Yes.
Then does that mean if you prepare 100 Gaia pi and 100 Gaia nucleus, then most of them will be transferred to the nucleus like that? Most of the pi's will be transferred to nucleus.
So you're looking at that way now?
No.
So it's doing this?
Yes. So according to your saying, I
Yeah.
think the pion to nucleus is much rapid than the nucleon to pion.
I'll say that the nucleus to the pion is more likely to happen.
Oh, okay. So then most of the nucleus will be transformed to pions.
Yes. Right. The cross section will be much bigger than that. This one than this. So basically, if you look at this, this is the thing. And suppose I'm operating the system with the same total energy. Okay. Suppose 100 GeV guy carry 2 electron volts. So 2 electron volts. But then 100 GeV plus 2 electron volts will turn into 1 electron volt mass electron. So most of them will be kinetic energy. So it will carry 100 GeV sort of energy. So this factor can be huge.
So I wonder, it might explain why some reactions or seems that it is irreversible in that sense.
Yeah. So all this factor will go into eventually, to explain why, at some point chemical equilibrium will stop. It's a very energetic system. Both ways can happen actively, but as you start losing energy or temperature in the context of cosmology, all of a sudden one directional process will stop. Only one particular direction will happen. So one guy goes, hopelessly annihilating the lighter guy. That's exactly what happened in cosmology, for instance. So this is the important factor. Another question. Good. Now we are gonna. So that's the end of this discussion about the cross section. Now we will move on to unitary. Not the full flat version of unitary, but something that we can say about unitary already. By the way, in the context of cosmology, that I said, at temperature above the 200 GeV, for instance, all standard models are there. They're all there, mixed up, and the electron is powerful enough to generate Higgs boson, or neutrino is strong enough to generate Z boson. It can do all of that, or Z boson can do neutrino. It will actually go back and forth. In that consideration, this is not sufficient. This sort of information is not sufficient, and there's an extra thermodynamic factor that that go into the discussion. This is called the thermal average cross section, not just cross section. And there's extra thermodynamic distribution function dependence. Okay, but kinematically, this thing is anyway there. So I'm saying, in addition to this, there is an extra disparity that comes from the thermodynamic distribution of the particles. Just to be clear. Okay, so let's talk about unitarity. So let me just check with everything. So, any questions so far? Good. With everything. So the discussion is optical here. I think the name comes from non-relativistic quantum mechanics context. But for us, today's discussion will show that what is known as optical theorem is a consequence of unitarity of estimates. This is extremely important and powerful thing. So you really want to get the physics out of it. So remember, S matrix is defined as if you have out state, and then if you have in state, we define S matrix as this way, and then it can be written as free version of that thing with S matrix, and the free version of each state like that. Okay, and then this is written going through all this discussion about the interaction picture, Dyson's formula, blah blah blah, and time order exponential of e for x, the interacting Hamiltonian interaction picture. So that was the thing. And clearly, this satisfies unitarity. So S matrix satisfies unitarity equation. At the end of the day, this can be viewed as change of basis from in a static state basis to the out a static state basis, which is done by some unitary rotation in order not to change any probability. Okay, let you. Okay, or if you like, you want to view that as some sort of time evolution this way. Either way, either physics way, it is unitary. So we're gonna now study the consequence of or implications of that unitary of this S matrix. And you may recall that S matrix can be written as trivial part, identity, which means that nothing happens, right? Plus part that describes something happens, which I put as I times T. And this corresponds to this calculus non-trivial dynamics. So in terms of that, let's study, and then I said one more thing that if I have F T I, okay, now I'm not gonna just put 0 0 all the time. Let me just write it away. This was the what's defining Feynman invariant. Yes.
Can I consider the one metric one in the metric, and can I consider the one in the just Dirac delta function?
Yeah, so okay, so this is an operator, so you can view this as identity operator. Now, now if you look at that way, now this will come out as a delta function in the gigantic space. Okay, in other words, it will depend on what's the dimensionality of the Hilbert space where this takes place. If this is the discrete finite dimensional Hilbert space, then this is finite, identity matrix. If this is the continuum infinite space, then this will be some ugly looking delta function, including not only that, but this and then all other states delta function. Any other question? Yes. Okay, so that was the relation of this thing. So now let's study unitary. So F dagger S is equal to what? 1 minus I T dagger 1 plus I T is equal to 1. Very good. So let's expand it. So I get 1 1 1 that cancels. So minus I T dagger and then plus I T and then the product. And then the product. T is equal to 0. So you can do this math so far. So this equation therefore can be written as minus I times T minus T dagger is equal to T dagger. Okay, so this is just trivial statement that S matrix is unitary, right? So far. Okay, so this is an equation. So let's extract the physics out of it. So in order to do that, let's sandwich this equation with some say F, some say I. Okay, so we know what to write down for T part. Let's understand what to write down for T dagger part. So let's complex conjugate this equation for that reason. Let's complex conjugate this equation, and that gives me I T dagger F from the left hand side, and the delta function part is real. Stay the same. And then amplitude with Fi. So the matrix element of the T dagger is a complex conjugate of an element, but Fi flipped, like that. Okay, let me say that again. T is associated with A, the amplitude, Fi order, like I to the F, I to the F. T dagger is a complex conjugate of amplitude, but Fi flipped. Okay, good. Now I can write down this equation. So let's start with the left hand side. First of all, there's minus I. I have this. And then there's gonna be 2 pi to the 4 delta function overall. So let me just pull it out. Take out of the whole expression. For the first part, that will give me Fi. Good. The second one that gives me SAR, but Fi flipped. Right? Good. Then that should be equal to F T dagger T so far. Okay, so let's study the right hand side. So in order to do that, I'm gonna plug in the complete set. Here, I'm gonna insert a complete set. The complete set will depend on theory, right? Some theory you only have like single kind of real scalar field. Or if you look at the different theory, you might have a fermion, vector boson, all kind of stuff. You might have a spin 2 particle. You also have some continuum stuff. It really depends on the theory, right? So since I don't want to specify the theory, I'm just gonna write complete set as this like real looking expression. So there's some and there's some integral, some say, which can carry continuum indices as well as discrete indices. So this is an extremely complex expression. But I explained to you why I'm writing this, because it's extremely theory dependent statement. So, but just to make sure, suppose I'm looking at the theory with only one kind, single kind real scalar. So then complete basis will look like, first of all, how many such single particles, like a 0, 1, 2, 3, 4. Whenever I have that, what I have to do is I have to integrate, because complete basis of a single particle will look like that, right? So this is the if I have a single particle, that is my basis, right? So this is the identity. If I have only a single particle, you have seen that. Yes, but now I'm talking about R number of particles. What that means is that I have to have, oh boy. Oh, good. So I have to 1, 2, R, very good. And then I'm gonna have that as my complete basis. But if I have R number of identical particles, especially if I integrate over the entire possible momentum, this will have a multiplicity, redundancy, right? So I have to divide it by some symmetry factor, taking into account the fact I don't want to overcount number of things. In other words, 1, 2 will be there, plus 2, 1 will be there, but if I integrate over all of that, they're the same thing, right? So I have to divide it by permutation. So anyway, it will look like something like that. Basically, how many number of which kind of particle, complete momentum integration, but then some symmetry factor. That is the structure. Is that clear? So that is captured by this beautiful expression. Everything is there. Is that clear? Good. Okay, nobody's happy, but I'm pursuing. Okay, let's do it. So with that, I'm gonna insert the complete basis, and that will look like very compact, nice expression. But you know, that is sometimes dangerous because you don't know what you're talking about. With writing something, you say, I don't know what it tells. Okay, so be careful. Okay, so now let's express this is equal to PM. Okay, let's see if I do it. Star that flipped and that. Good. And then this part gives me 2 pi to the 4th delta PM PI and then M1. So now since you have a 2 delta function, that factor can be written as one factor looks like basically total momentum delta function with PM of PI. Because this is equal to that and that is equal to that. So F is equal to I. I can always pull that up like that. Now that is independent of the PM, so I can take that out of this complete sum. And then I have what? So MF star MI I 2 pi delta PM. Yeah. Okay, so almost there. So now we're almost there to understand the physical meaning of that. So at this point, we can cancel out this overall delta function, momentum conserving delta function, and then let's write down the rest of it. What do I have? So minus I. What do I have? That's the left hand side, and the right hand side is star. Okay, so that's the answer solved. Right? So this is true in general, meaning whether or not I study theory in perturbation theory, right? This is non-perturbative answer, right? I haven't said anything about perturbation theory. So now, in order to extract something useful, this is already powerful, and sometimes we do use this full version of unitary. Okay, but one can extract slightly more intuitive information if I restrict myself a little bit. Okay, so this is true. But now let's consider, and that is anyway. If you're curious what I was trying to say, I'm not gonna say. Take the QFD2. Anyway, so let's consider elastic. By the way, with QFD1 covered, you're not quantum field theory. I'm sorry, because you haven't touched the quantum part of it. Only the second semester we consider. Oh, the second part of the QFD will actually talk about quantum aspect of field. Anyway, so elastic forward scattering, which is very true, by the way, really true. Anyway, so let's talk about elastic forward scattering, and that one was what? Like I is equal to F, right? So if you put in electron comes out. Okay, the same way. Why is it called forward? Because it goes in and then it only gives a very little momentum kick, almost nothing. It keeps going, so it's going forward.
Oh,
okay, so that's
they just
like very tough to continue to go. Yeah, so that's the forward elastic scattering limit. So if I do that, what do I get? So what do I get is minus I times I minus I, well, no summation, okay? You have a disease, right? Whenever you see this, there's a summation, no summation. Therefore, any text we have to say there's no summation now. Everybody's diseased. So now let's finish up this part. Okay, so that is the expression. Now, this is not a very useful expression. Let's explain. First of all, this is equal to what? 2 times I times imaginary part of the I amplitude, right? Okay. At this point, it's a problem. Let's understand what this is. So what that is that recall cross section is given by, first of all, there's initial part 2EI, okay, the amplitude square, and then D, right? Oh, no, you should say you should have yelled at me by now. Nobody did. Where's my blocks are? And then amplitude square and D. And so that is missing here. But this was what? This is what nothing but momentum delta function times for each finite state particle. You have to have this Lorentz theory measure. I told you that this thing is exactly that kind of thing for all finite state now, right? For n state, which is now appear to be, we did an example like I to the n or summing over all n. So that's finite state here. And even excluding correct symmetry factor if there's identical particles. Okay? What is missing therefore from this side is that this is therefore same as 4 times E1, E2, E1 minus E2, or if you like, the center of momentum frame. I told you that this is the same as that. And then cross section. Cross section that goes from the I to M, but then now this completeness relation is the crazy monster because it not only includes a fixed number particle, but you consider all possible particle combination that is allowed by quantum theory. So now this is some entire possible such particle. Okay. So far we played with expression. Now let's take a moment to extract physics out of it. Okay. I'm taking a pause, but now let me write one neat expression. So left side canceling the factors of 2. Imaginary part of the sum amplitude I goes I is equal to 2 times, because 2 cancel, ET times initial momentum, that is basically free factor, and then total cross section or inclusive cross section. This is so far this is the result. I haven't explained to you the meaning of it. Now I'm gonna spend the rest of the time today to explain the meaning of this. Again, there's a makeup quiz. This place, this time, for something.
We have a piece.
What did I say? Quiz?
You said make a piece.
Oh, did I say makeup quiz? Probably I have that in mind. No, I never mentioned that.
Oh.
Makeup class. Okay, makeup quiz means that we were supposed to have a quiz, which means there was a makeup quiz. I never had a plan to have a quiz so far. So makeup class. Okay, 2502, second floor. Okay, 7:30 until sometime. until my voice survives. So now let's extract the business meaning out of this equation. Well, now you can read this equation, yes? I don't mean immediate part of A of I, no. You can read the meaning of this equation, but let me deepen that. So in order to do that, let me draw a diagram that captures this equation. Okay, I'm not going to worry about this brief diagram too much. So consider a diagram, say you have something, I don't know what's happening inside, right? But let's take the particular example. So this is an example, okay? So let's consider a diagram that looks like this. And then he said, oh, I'm looking at eye to eye. I draw a diagram intentionally that has the same initial and final state, right? Now we'll look at the immediate part of that thing. Okay, immediate part of that thing. What does that even mean, right? And then he says, oh, that is the same as, so basically first, you do what is known as a cut, the diagram. Technically, it's known as a Katowski cut rule, but for now, if you're super curious, wait. Okay, but for now, try to cut it like that through the center of the diagram that divides initial and final state. So the cut must be able to distinguish initial from the final state. In this particular example diagram, this is why you cut. Okay. So if you do that, so then there's some intermediate state that appears in the middle of this diagram. So M. In this case, the M has two such nuclear and anti-nuclear states, for instance. Okay? So therefore, it says that the immediate part of that thing is the same as, like same, I mean tilde, sim level, that this is inclusive cross-section of that goes to some final state. Here it is not specified yet, but in this concrete example, it actually specifies. So it goes to nuclear and anti-nuclear. Okay, all two kinematic. Okay, so that's literal translation of that thing. Given any diagram with the same initial final state, if you cut it, the major part of that blob is the same as looking at the cross section associated with that process. That is the statement. You might say, oh, is that crazy or reasonable? Well, first of all, better be reasonable because it's derived. But now you have to appreciate the meaning of that. So one extremely important aspect of this unitary equation is the following. I'll explain slow and shortly. But let me first make the statement. Unitary. So let's consider perturbation theory. Okay. So perturbation theory. So for instance, so this is I'm looking at the geometry of order, right? This is the geometry of order. This is. You can ask, oh, do I have pi to pi sort of diagram at the lower order in G expansion? The answer is no. Convince yourself. Okay, so this is the only interaction that has this theory. In order to create the pi goes to pi in the connected case, this is the first diagram you will encounter. Okay, this is the lowest order in G expansion diagram that get you a connected diagram that can describe pi to pi. But obviously you can go higher order. So for instance, let's see, can I be image? Okay, so I can have like that, for instance. Okay, this is a G to the 6. Oh, whatever. Okay, we can do it the other way around. This is cross version of it, right? Or you can have go even higher order. Like that too. Okay, keeps going. Now I want to make a comment, important statement. Before that, if you cut this diagram, obviously this now will describe imaginary part of that thing if there is same as pi goes to nuclear, antinuclear pi here. Let's keep doing it. To cut this, pi, this imaginary part is the same or related to the total cross section of pi to nuclear, antinuclear, and then another nuclear, another antinuclear. The 2 to the 4 process. And so on and so forth. Now I'm ready to make a statement. This is extremely deep and important statement. Unitary connects a physics at a lower order in G expansion, which is G square physics, right? Yes, you're computing cross section, but the physics happening at G square. So I'm looking at this side of the diagram. Okay, you can draw amplitude at G square. There are 2 vertices. Okay, unitary connects the physics at lower order in G expansion or perturbation theory expansion to a higher order, now G to the 4th, but only through the imaginary part. So it's like, if you like, iteration process or recursive process. Okay, so what is the recursive process? It's called the bootstrap in modern language. If you're given information about that base, like G to the 0 or G to the square information, you can ask yourself whether from that information I can extract information about high order of physics. Okay? Suppose you're given, somebody gives you this information. They can ask, oh, can you tell me about anything about higher order in perturbation theory? You might say, what do you mean? Just draw another diagram on your own, just compute it. Don't ask me that. But unitary captures secretly information about the higher order information, G to the 4. But not the full information, but only the imaginary part of that information. You can ask, oh, that's pretty, but that's great, first of all, because you get some information as a bonus, right? Once you understand unitary. Unitary links like that, okay? Lower order in perturbation to higher order like that. But only through the imaginary part. You can ask, oh, what about the real part? Then it would be fantastic. It looks like I can just reconstruct the theory if I have this information, right? Okay, is that a good question, first of all? If that's a good question, let's see. Should I tell you the answer or not? So, causality, fill that in. You must, oh, how? I'm not gonna tell you, because you must be super curious. It is through what's known as a dispersion relation. Okay, so that's the quick answer. Maybe I'll discuss next semester, maybe not, but this is the first blow. Okay, and then let me make this semester slightly more careful now. Through the window of the 2-point function. But any questions you might do. Is the statement clear? G square order diagram secretly captures the imaginary part of G to the 4th diagram. That's what I'm saying. G to the 4th diagram in principle can capture something about higher order imaginary part if you like. Okay, so it has this recursive structure. You have a question?
In this case, we consider the I to I process.
Yes.
In the scattering matrix, in the T is the S minus 1.
Yes.
The 1 is the I to I process, I think.
Oh,
So I think that can be some count the process.
one is literally trivial process in a sense. This actually goes to I, but there's something non-trivial happening. But if you like, can I draw a diagram that comes from the 1 in the S matrix? So that is it. So I literally goes to I, like pretty fast. Nothing happens. So this is different or distinctive from that. So this is really captured in T. This is from 1 in S. Did I answer your question?
Yeah.
Yes. Any other question? Okay, that's good. So I want to talk about the 2-point function a little bit. And introduce wave function terminology and put things in the context of this discussion, and that will be probably end of first lecture today. Okay, so let's understand unitary equation, which I completely erased. Wow, that's fantastic. At least I should have kept something, right? Where do I start? So minus I. Okay, so that is the general, so not general, but unitary equation, right? Okay, for that for process. So now let's consider one-to-one process, meaning propagator. So here I'm going to consider pi to pi propagator. That I can, in the momentum space, I can write it as minus e, which I will write just like that. So what is this? This is 2-point function, 2-point function, but in the momentum space, which you can get from the 2-point function in the position space by Fourier transforming to the momentum space. Okay. Now, what is the diagrammatic representation of this thing? So you first have this, right? So pi goes to pi. Remember, pi was the excitation of the field phi. Right? Continuously checking whether you're focusing on the lecture. Okay, so pi to pi, it is that. This is order G, 0 to 0 4. Right? You know vertex. You can ask yourself, we are doing perturbation theory. Can I have correction to this? Right? You can ask yourself. Okay? Can I draw a diagram which is a perturbative correction to this diagram? What does that mean? Do you have any? From any? Does that look like pi to pi now? Diagonally? Yes. Okay, good. That's good. Right? Good. Since you can insert one, why not two? Right? Since you can insert, since you have two, why not three? Or you can have something like that, which looks as nice. And a lot of all the instructions of that diagram and many other possible stuff here, right? So this is how you start building up possible perturbative corrections to usual propagator, which looks like this sort of like that square. Over that thing, we like placing that. We can ask, okay, let me compute this, that is a correction to that. If you're a powerful computer, you can also do the high order calculations, we do this kind of high order calculations for all possible directions. Now, there's a problem with this program. There's a problem with this program, naive problem. I mean, problem if you think naively. And we will talk about that. But for now, let's just look at this box. Okay, each of this box. And then let me call that box to be just minus I times something. And let me call just capital sigma, which is a function of this. Okay, so I don't want to compute it now. Okay, you will learn how to compute it carefully and extract all the physics under the program of renormalization theory. Okay, you have two class. For now, let's say that is given. And then let's study the meaning of it. So first of all, if you want to compute that at a G squared order, so this object is order G squared. Right? Obviously, because you have two verses. And then there's a momentum dependence. Now let's discover the problem. So the second piece, the first piece goes like 1 over p squared minus m squared. Let me drop ISO for now. And then that diagram consists of like first propagation, a little bit of propagation of pi times this intermediate box, but without including propagator of external x. So I put this cutting line, and then ended up with the propagation. Does that make sense? So this thing consists of propagation, which is the first part, middle box, which I should not include this propagator because I already included it, and then the final propagator here, right? So let's try to write down. So this looks like 1 over p squared minus m squared, that's the first bit, times that is minus I sigma I told you, times that propagator I over p squared minus m squared. Good. And then if you look at the that series sum along that direction, this is like the usual like zero order propagator times 1 factor of that thing, 2 factor of that thing, 3 factor of that, and so on and so forth. It's a geometrical sum series. Okay. Now, what is the problem? What is the problem? Is this perturbing the small fraction to that? That's the question. Because I know that I'm doing the perturbation theory in the G, so higher G power means small. That's why I can trust my calculation only based on low order in G calculation. But what if this is as big as that? What if this is even as big as that, as big as that? Totally bogus. We don't know what we are talking about, right? Because unless you finish the entire computation, you cannot say anything about it. So the question is, do we have a sense of a perturbation theory? Let's check here. Okay, so this is order G squared. Aha, must be small. Yeah, Professor, I know I'm doing perturbation theory. So for that, let me say this is a parametrically small. Parametrically small, I mean, there's a parameter that defines perturbation theory, and this is suppressed by powers of that expansion parameter. That's what I mean by parametrically small. Now, I want to compute this two-point function, thinking that I'm going to the regime of on-shell. So this goes to 0 here. Okay? I'm computing this propagator, thinking that I'm going to go on-shell. Now, if I go on-shell, on the other hand, this blows up. Right? So as I bring the piece closer and closer to the m squared, this factor becomes larger and larger. So this is kinematically enhanced. So there's this blood competition. Okay, I really want to suppress you because I'm like G to the high power. Okay, try your best because I'm gonna kinematically enhance this thing. I'm gonna blow you up on the other hand. So this competition makes unclear that whether this is actually a small factor multiplied on top of a 0 order propagator. Okay. So what do you do then? What do you do then? So here is the answer. Therefore, this way of thinking about the perturbation theory is ill-defined because this may be as big as that. This may be as big as that. So in order to address this problem, we have to do what is known as a resummation. Resummation means that let that sum anything. Since I don't know which one is larger or smaller. But what do you mean? Okay, then can we still do perturbation theory? So what I mean by that is the following. Okay, so don't be panicked. So p squared minus m squared I, that's 0 order. 1 plus we have minus I times I is just 1. So hold it already. So it is that structure, right? Now let's choose a momentum for a moment where this is actually smaller than 1. Okay, so let's first go to the momentum in the complex plane of momentum where this is actually smaller than 1. And then let me resolve, meaning that then I can 1 plus x squared plus and so on becomes 1 over 1 minus x if x is smaller than 1. Okay, so let's go to that regime, and then that becomes that times 1 minus sigma over p squared minus m squared. Okay, then this becomes I over p squared minus m squared, which was original 1, and if you will multiply minus sigma. So instead of multiplying the sigma as a numerator, you have to resummate that in such a way that sigma appears in the denominator like that. So once you get to this form, then you can analytically continue the momentum value that comes in such a way that you can go out of the region where this can might be bigger than 1. Okay? So now I'm running out of time. So I just tell you the information, and then this evening, I will finish up this discussion, making a connection to the first unitary, and then you will see from this discussion that the concept of wave function renormalization, mass renormalization, and decay rate will come out. Okay, so that will be the end of this part of the discussion, and then we will move on to green function. Okay. If you have any question, I'm happy to address outside of the room. I have the audience.